studying the lives of marine mammals from Santa Cruz. A student-conceived reactor that makes energy from trash. But first, students from across the country bring their scale model buildings to a seismic design competition in San Francisco. All on this edition of OnBeyond. April 18, 1906, one of the worst natural disasters in U.S. history. About 300 miles of the San Andreas Fault moves as much as 28 feet. The Salinas River changes course, permanently, by 6 miles. Unreinforced brick buildings crumble like so much sand. San Francisco and nearby cities are laid waste, and ensuing fires ravage thousands of wood frame buildings. Over 3,000 people lose their lives. Back then, our understanding of earthquakes was meager. While predicting earthquakes remains unattainable, our ability to prepare for and mitigate quake damage has advanced greatly over the last century, and promises to improve into the future. That's because here, 100 years later, students from across the country have come to the Pier Undergraduate Seismic Design Competition to test their ingenuity at designing seismically robust buildings. With support from the National Science Foundation, the competition was conducted by Pier, the Pacific Earthquake Engineering Research Center, along with EERI, the Earthquake Engineering Research Institute.
The Pier Center is a collection of universities and industry partners working together to develop what we call performance-based engineering. And performance-based engineering is all about how to design structures, taking into consideration the real ground motions that are expected, real behavior of the structure, and ultimately how it performs. So we can build structures that'll perform the way society and owners want them to.
I think it's a great opportunity, for these students to be able to participate in this 100th anniversary conference, not only for the competition and for the design aspects, but also to be around a lot of the acting professionals and practitioners to see what it is really like on the outside world and get a view of what it might be like once they graduate and go to look for a job in industry. What I like to see as a faculty member is that the students get to apply what they're learning in class in a practical situation, and then they get to see the results. They spend a lot of time doing computer analyses and hand calculations, but here they really get to look at, they really get to see how their structure performs. They get to analyze it and then see how it works.
To address the goals of performance-based engineering, Pier challenged teams to design a multi-level office building that would not only survive some of the worst earthquakes recorded, but also achieve architectural and economic excellence. The buildings were constructed of balsa wood and glue. Built to 1/72nd scale, the buildings are limited to a height of 2 meters and a footprint of 18 inches. This makes each story scaled to about 12 feet high, with about 38 floors total height. Mechanical dampers were allowed, and at least one team used them as a structural element at the base of their building.
This is our foundation system, and it's a damping system. There's a cork casing that encompasses the columns, the shell columns and the core columns. And essentially the columns aren't actually attached to the base plate, just the cork system is. So the column sits within the base plate and is allowed to sort of rock back and forth as the structure moves, causing friction between the cork and the column, and it dissipates some of the energy.
Some used internal shear walls in the core of the building.
I feel that ours is going to be a winning design because we've simplified it and not made it too complex. We basically have a shear wall core in the middle that carries the load. The exterior, all this design on the outside, the spiraling effect and things like that, is not structural at all. All the structural load, the weights and everything are carried down through the shear wall. So the aesthetics, we could get really intricate with the aesthetics and things like that because they're not really carrying the load.
Designs varied, from straightforward and robust to graceful. Students worked diligently on their entries and took a variety of approaches to address the many considerations of performance-based design.
We realized that to increase the floor space, you have to make the building square, and we figured everybody else is going to do that, and that's not really an architecturally, it's not different. Everybody else is going to do that. So we decided to go with the octagon. Although that would sacrifice some of our floor space, we figured we could win on the architectural part.
Our performance is based upon minimizing roof acceleration and drift ratio of the entire structure. We're basically trying to put a soft story to roof isolate the roof acceleration. So what we have is pin-pin connections on the top, so that makes the roof very flexible laterally, horizontally. And then we place these dampers to damp out energy. Now the problem with that is we need some sort of returning force so that after the motion, the soft story will have to return to its center equilibrium point. Now with just the damper, that's not enough returning force. So what we had to do was put springs in an angle on the dampers so that it will provide some returning force. Now the problem is that we have to find a balance. The more stiffer that we make the springs, the more stiffer the soft story will be, so it will be less effective on damping out energy. But we want the springs to be stiff enough so that it can return to equilibrium.
These are braces, and they are pretty much just for show. They don't add too much structural significance. The most, I think that has the most structural performance is the columns that go up and down. They pretty much are the strongest element. These are pretty thin. We worked with architecture, and they just told us, if we stick on a nice diagonal, it gives it some character, and it's pleasing to the eye, and I think that's important too.
Instead of just a rigid cross brace, which makes the building stiffer, where it connected, we decided to put a piece of sandpaper in there and allow the joint to move and actually be open, and the sandpaper will create a friction that'll take energy out of the building itself, so it won't move as much in both directions. It might slide in one direction, but as it tries to move back from the earthquake displacement, it'll actually end up losing energy and slow itself down just by the friction within the joints.
The winner will not just survive the quakes. The team with the highest annual building revenue wins the competition. This revenue is derived from a combination of construction costs, costs of damage and losses, and revenue from usable square footage. A huge component of the challenge is the technical presentation, where the students must clearly articulate their design rationale and show how they arrived at it.
So what we did is we devised a constant floor plan that rotates around the shear core in 15-degree increments, which provides a complex structure that's still very elegant. For the income, we used a floor plan that maximizes the maximum allowable space, resulting in a floor plan of each level has approximately 0.115 meters squared, and the total is 2.94 meters squared. As you can see, we've punched door holes in the shear core, allowing the interior core to be used to be counted as usable space. This results in a plan that brings in a little over $1.84 million per year.
Another feature which enhances the aesthetics of the building are the diagonal members, which draw the appearance together and attract your eye upward along the height of the building. Of course, the most interesting feature of the structure is not the appearance, but the structure itself. Our building utilizes an innovative decoupled system in which the inner core is designed to be more flexible than the outer floor system, and both are independent, joined only by dampers, which allow them to play against each other and cancel out each other's movements, reducing damages in the structure.
Our major focus was on the construction method itself, because in our past modeling we know that failure happens in a joint, and there's a lot of joints in the system, and in order to have the redundancy in the building, we had to ensure that we made a quality joint. So we notched each beam and created half-lap joints and cross-lap joints, which are less of a mess to create, and they're more aesthetically pleasing than a butt-end joint with a gusset plate.
We are focusing on costs, right? As everybody here is focusing on costs because money moves the world. But I tend to disagree. I think innovation moves the world. So what we're really trying with our structural elements is we're trying new concepts. We've seen shear walls, we've seen cross bracing, right? So we're going to try something different, something more innovative. We wanted to focus on architecture, focus on space. Our design is based off of two things. It's based off of a core, which supports all our gravity loads and lateral loads, and it's based off a non-structural shell.
In the final analysis, everyone is here to see the buildings perform in quake testing. To do this, the models are placed on a shake table which will replicate the ground motions of 3 devastating quakes: the 1940 El Centro, the 1994 Northridge, and the 1995 Kobe earthquakes. Metal rods are added to simulate building loads. At the top and bottom of the models, sensors are placed to reveal 2 important parameters in calculating damage: roof drift, or how far the building sways, and roof acceleration, or how fast it sways. A combination of these measurements helps the judges determine how well the building performs. You can imagine if a building drifts too far too fast, that things inside are not going to fare well in an earthquake. With that, the testing begins.
This structure we're going to shake first with the 1940 El Centro earthquake. Okay. The next earthquake is the 1994 Northridge earthquake. Okay. Our next earthquake is going to be the 1995 Kobe earthquake.
Kobe earthquake. Go.
After being subjected to the required quakes and recording the performance data, the organizers put on a show. The models were taken to extremes, both rapid violent shaking and something called a sine sweep. A sine sweep finds the building's natural sway frequency and then repeatedly subjects the structure to that frequency. It's much like an opera singer's voice breaking a wine glass, and sometimes the results are unmistakably similar.
Okay, the team said they don't have a box to ship it back to Washington. So we're going to go ahead and just shake it at its natural frequency and see what happens.
However, in some cases, student ingenuity and design trumped the best efforts of the shake table and survived the demolition derby unscathed.
Okay, are we ready? Okay, here we go. Stand back.
Down. Yeah, look at the dampers move.
All right, I think somebody's beaten the shake table. Eddie?
We're taking it home.
I think we've been beaten. Well, I guess the grand champion, the first place team of the 3rd annual Peer Seismic Competition with an annual rental income of $2.25 million a year is another peer school, University of Washington. You did a great job. Good job.
Thank you
Congratulations. Good job. Thank you.
While the University of Washington was awarded first place, in the end, every team was a winner. Students had an invaluable experience, putting theory to the test and making their ideas reality.
UC Santa Cruz is one of the top centers for marine mammal research in the world. The campus has a unique combination of field sites and laboratory facilities for marine mammal research, including animal holding pools at Long Marine Laboratory, and ready access to natural populations of marine mammals in Monterey Bay and at the university's Año Nuevo Island Reserve.
Well, the Marine Lab is the university's sort of coastal outpost for marine research and the kinds of things that we can't easily do on campus where we need running seawater. So the study of nearshore organisms, the study of marine mammals where we need large amounts of tank space and pool space, a good supply of running seawater. And then we have a whole public education program that tries to take the research the scientist does and bring that to the public, grade school kids, their families, so that we all get a better understanding of sort of how the marine environment here that's so important to us works.
Biologist Terry Williams is working here to answer a fundamental question about marine mammals. What does it take for a mammal to make a living in the ocean?
We're interested in basically what makes a dolphin, and then what a dolphin would need to survive. Our research program tries to do two different things. We've got sort of the up-close physiology, biology of these animals that we do in a controlled setting like this, and then we want to know how does that really work out in the wild? What does a wild dolphin need in order to make it? So we work all over the world on animals from the Antarctic to the Arctic, and for the dolphins, the wild work is done in the Bahamas. We've been looking at whether temperature per se is a big factor in these animals' lives. How much do they need to eat at during different seasons, and then how much of a metabolism change can we expect? And again, because of the idea of global climate change and water temperature changes that we're certainly seeing off our coast.
Williams is also studying California sea otters, which have made a partial recovery after being hunted nearly to extinction. But Williams wonders if our coastal ecosystems still have everything sea otters need to survive and to thrive.
There's a huge question about California sea otters right now. How come the population hasn't just zoomed through the roof? Something is holding the sea otter back. It's very hard to work with otters in the wild. So what we did was convert the water tower over at Long Marine Lab into a simulated ecosystem for sea otters. The whole idea is, what does it take to be a sea otter? What are those energetic needs? And does the California coast really have what otters need in order to survive and for populations to increase? One of the things that my graduate student has found out, this is work by Laura Yates, is that the core body temperature of sea otters just fluctuates wildly during the day. Their core body temperature is going up after they're eating, and then it just starts crashing down as they're resting. And it gets to a point where they have to go and eat. If they don't go and eat and sort of stoke up that metabolic fire again to increase body temperature, they could potentially have a core body temperature that gets lethal. What that means is that the availability of food, always having it there, is just critical for these otters. You know, if it's not there, temperature's going to decline and they'll disappear.
When the tail gets very small, it means the animal's not moving.
Biologist Daniel Costa is using the latest in satellite tracking technologies to study the amazing annual migrations of elephant seals and other marine animals.
This is our latest and greatest technology. This is our GPS tag. This measures where the animals are to within 5 to 10 feet. This also gives us information on what the animals are doing in terms of where they're diving, how long they're diving, how deep, and their general diving pattern. you couldn't put this on a sea otter or some sea lions, so we use a tag like this, which is much smaller, but it gives us much limited amount of information. It tells us just where the animal is.
The tags are harmlessly attached to the fur on an animal's head or back and fall off when the animals molt in the spring.
So elephant seals have been a long-term animal that we've studied here. And in the last 10 or 15 years, we've been able to take that research much further. Instead of just seeing what the animals do on the beach, which is pretty much what we're limited to, the sort of computer generation has taken over, and we've been able to put radio tags first and satellite tags and time depth recorders. So now we've got an unprecedented view of what these animals are doing when they're at sea, hundreds, thousands of miles away from Año Nuevo Beach.
Research on elephant seals and other species has enabled Costa's group to identify hotspots in the open ocean where marine mammals from elephant seals to albatrosses go to feed.
We've got this program called Tagging Pacific Pelagics. We're tagging 23 different species of marine mammals, birds, sharks, fish, one species of squid, whales. So one of the things we're trying to do is take this away from the point of view of just what do elephant seals do to what do marine vertebrates do and where are the important areas in the ocean where the marine vertebrates are going to feed. These tracking technologies and tracking large numbers of animals are certainly leading the way to figuring out how to better conserve the ocean in areas that we can't get to otherwise.
We are in an incredible position being on the edge of the nation's largest national marine sanctuary, but not only is it incredibly productive biologically, probably the greatest diversity of marine mammals anywhere in the world, so that provides sort of the perfect environment for the scientists, whether it's the elephant seals at Año Nuevo, the sea otters. We don't have to go thousands of miles necessarily to study these animals. We've got them right here in our backyard.
Reporting from Long Marine Laboratory in Santa Cruz, this is Romney Dunbar.
Seven years ago, Joe Norbeck, former director of UCR's College of Engineering Center for Environmental Research and Technology, had a problem. The center had just completed construction and testing of a new high-temperature reactor designed by the United States EPA to convert wood chips into methanol. The reactor did not work to the level needed for commercialization, and while this was a setback, the failure inspired Professor Norbeck to think outside the box, so to speak, concerning the remarkable potential for reactors such as this to help solve the world energy crisis. He had a hunch, and 7 years later, the results of his hunch have proven considerably more successful. This is Lisp, the humbly named Laboratory Integrated Systems Prototype, a product of UCR's unique culture of integrating undergraduate, graduate, and faculty resources in major research projects. Lisp is capable of continuously converting any carbon-based material, from grass clippings to car tires to polyurethane foam, into very clean diesel fuel, while creating no pollution and generating excess steam for electric power.
We had 4 very bright undergraduates that came to me and said, we'd like to work on a project on energy for our capstone course on engineering design. And I had an idea of modifying the system that failed in what we consider to be a more versatile and unique way. Overall, the process consists of 4 steps. The first step, as we had said, is what we call steam pyrolysis. And I use the analogy that it's like putting tough meat in a pressure cooker and heating it for a while and it gets soft. That prepares the material for when you bring in hydrogen, it converts it very quickly to methane. And so the next step is to take the methane and do what's called steam reforming to convert that to CO and hydrogen. And then that you put into a catalyst and you make liquid fuel. So the challenge to the students was to see if this would work. We didn't have any laboratory to do that, but they had computer models that we were going to utilize, and off they went. Well, after the 2 quarters, I remember sitting there in the audience while they made their presentation, in which they said, if you take half of the wood that goes to a landfill, we can replace a major portion of diesel fuel in LA from waste, and we can do it for 65 cents a gallon. And I then immediately said back to them, first of all, you got an A+ in the class, and secondly, put an invention disclosure on this.
Engineering undergraduates have been central to the success of the Lisp project since the beginning, helping to solve myriad technical difficulties in the effort to successfully integrate Lisp's complex series of chemical reactions.
This job gave me an opportunity, everything I learned in class, to apply in real life. My job was to run this and see all the limitations that it has and what we can improve on for a newer reactor and a bigger reactor. Because one of the reasons we wanted to improve this is because our future plan is hopefully to build a pilot plant. So what I was doing is giving them all the results. Based on these results, we were able to calculate the new diameter, height, and all these things that is necessary to build a new reactor.
Professor Chan Sung Park, a senior partner in the project, helped solve one of the most difficult of Lisp's potential problems, maintaining high pressure throughout the system while taking in raw material and producing fuel continuously.
It looks like a very simple thing, but actually this is the most hardest engineering challenge, because our reactor is very high pressure, and our feed in our world is just 1 atmosphere. So we have to overcome the pressure difference. So we ended with make a slurry with the water, then we can pump it. That there is so many kind of the technology already developed for the pumping against the high pressure. So we decided to use that technology so that it works.
Lisp holds great promise for an energy-hungry world and has the potential for drastically reducing household, industrial, and human waste as well.
This is the shredded tire coming from the spanded tire. This is the agricultural residue. This is especially the bean. This is the wood waste. We shredded wood waste into the particle and we try to gasify it. This is the polyurethane foam. This is the coming from the car seat. They use the polyurethane foam for the cushion of car seat. This is if you go to the wastewater treatment plant, there is lots of the sludge deposit in the facility. We take the sludge and we convert the valuable fuel. This is the coal. Coal is regarded as the inferior fuel compared to the oil because this is solid, but we convert this solid coal into the liquid fuel.
This technology can be used throughout the world. And if you have a country such as Thailand, some areas in South America that have a lot of biomass, you now have a readily available feedstock generated from removing CO2 with sunlight to make fuel. So you don't have any net impact on global climate change such as CO2 emissions. So it's a pretty exciting, promising technology that started with a failure and 4 undergraduates doing a project to graduate. And it's been an interesting experience for us as an organization, and it demonstrates the quality of our students.
For UC Riverside, this is Jim Brown reporting.